and I will introduce you. Okay.
One moment, I'm unmuting, I'm starting my video, and I'm sharing my screen.
Okay. So Lorette Tuckerman received her PhD in applied mathematics from MIT in 1984. She spent a decade at the Center for Nonlinear Dynamics at the University of Texas in Austin. She accepted a position at CNRS, Centre National de la Recherche Scientifique in France, in 1994. Her research field is hydrodynamic instabilities using computational fluid dynamics. She has investigated bifurcation scenarios resulting from rotation and from convection, and she has also worked on transition to turbulence. Concerning the Faraday instability, this is a problem for this plenary talk. She was the first to carry out a linear stability analysis of the viscous problem, and the first to carry out a nonlinear three-dimensional numerical simulation. This paper about this instability is very well cited. Okay, could you please start your talk?
Thank you very much, and thank you for this invitation. Can everyone hear me?
Yes, we hear you and see you.
Okay, if I go too fast, Tatiana, you tell me to go more slowly, okay? You motion with your hands. Okay. So I start here with a picture of a numerical analysis, numerical simulation of Faraday waves. And these are my former students who've obtained most of the results I will speak about. And these are the authors, the three authors of the code that was mostly used. So I begin by telling you a little about Faraday. This is the same Faraday as electromagnetism, as Faraday cage. Of course, often people are confused about this, but I think in an audience of hydrodynamicists, you will know that Faraday did important work in hydrodynamics. So here's a layer, a fluid layer that is shaken vertically here, and he observed in 1831, or published in 1831, that on this layer appeared standing waves. And here are some typical patterns of stripes and squares and hexagons. And here is a film of our numerical simulation of the square pattern here. And I've been very fortunate in this Faraday experiment because historically, although Faraday did these experiments in 1831, unlike other hydrodynamic stability problems like convection, Rayleigh-Benard convection, Taylor-Couette flow, which were actually experimentally studied later in the 1890s and early 1900s, they were analyzed theoretically by Taylor and by Rayleigh in the 1920s or so, 1910s, 1920s, and simulated numerically in the 1960s. Whereas there was a important delay in analyzing Faraday waves. The inviscid linear stability analysis was done by Benjamin and Ursel in 1954, so long after the Taylor-Couette and Rayleigh-Benard analyses, and the viscous one done by me in 1994, and again, long after Rayleigh-Benard and Taylor-Couette, and these numerical simulations were done only in the 21st century, unlike the those of convection and Taylor-Couette flow. So here are some of these early results. That is to say, this is the result of the linear stability analysis of Benjamin and Ursel in the inviscid case and ours in the viscous case. Let me explain to you what this is. For different wave numbers, K and amplitudes of shaking, you have instability of the harmonic and subharmonic type at these values in the parameter plane. Let me show you a little demonstration of what harmonic and subharmonic means. I'm sure many of you know, but I enjoy doing this demonstration. Here is the shaking of the fluid layer, and subharmonic goes like this. whereas the harmonic goes like this. So harmonic has the same period as the original shaking, and subharmonic has twice the period. And as you can see for the viscous case, the tongues are lifted and are rounded. And here is a little picture from the squares, from the simulations that you saw before. And let's see, what is this? Yes, okay. So the numerical methods that we use are, the code was written by my collaborators. I really, although I am a numericist, I don't know anything about free surface codes. So I really am just a user for this, just a consumer. And here is the general idea. It's there's fluid everywhere, above and below. And the domain is meshed in a cubic way here, the whole domain, but it has different density and viscosity above and below. And then the surface is meshed with triangles here. And this is the equation, or this is just Navier-Stokes with a variable viscosity, as you see. And this is the surface tension and how it enters the velocity. There's interaction. The surface is advected by the fluid, and the fluid reacts to the surface tension. So that's the interaction between the surface and the bulk problem. And these are this front tracking method. The names associated with these methods are Trygvason and Peskin. And then here are films. This, you've already seen the square one, and here is a hexagonal one. And the hexagonal one I'm showing a little longer. You see one surrounded by 6. You don't see, it's periodic. These simulations are done with periodic boundary conditions. So you should think of there being another one, another bump over here. So the first exotic pattern was found on this hexagonal pattern. And here are colored, very brightly colored visualizations of the interface over one period, one oscillation period. Here you have the centers of the hexagons being very maximal, and here you have them being very minimal here. So this is over a period, a total period of t, and this is how it varies. And so this is then the amplitude, the height, the maximum height over a period of the hexagonal pattern. And these 4 points here in time are those 4 points you just saw. But this is now the envelope. And here, here's a visualization, the same visualization you saw before, but now shown in flat here in a contour plot over here of these 4 points. And my student, Nicolas Perinet, who obtained all these results, we were satisfied, very satisfied that there were hexagons, but he wasn't satisfied and he kept running. And look what he saw. Indeed, he was right to keep running. The hexagons became this other pattern, which we call beaded stripes. They're like stripes, but you see they have these little eye patterns here. And so we thought, okay, well, he was right. It's not hexagons. Beaded stripes are the final pattern. Again, I'm showing you 4 pictures because of this is t equals 0, t over 4, t over 2, 3t over 4 during one Faraday oscillation period. So he was right, but he kept running. And what he saw was another transition now to these things that looked, again, a little more, they don't look exactly like hexagons. They have less symmetry. You can see that although you have 6 white objects around a central one, before they were circles, perfectly symmetric by reflection in any of these axes. Here, that is not true. These are kind of triangles pointing to the left, and these are kind of triangles pointing to the right. You see it has less symmetry, but it looks more like the hexagons than the beaded stripes. And you can see that that one's not finished. It goes back to being like the beaded stripes, but not exactly. It's slightly less symmetric. And then we got this pattern again, these quasi-hexagons, but they're not the same because since this period means something, 0 to t, that is to say, there's a certain phase by which we're oscillating. So it means something that this happens in the last picture and that this happens in the second picture. And so these are a version of this, a different version. It's got a space, there's a spatio-temporal symmetry between this pattern and this pattern, where you shift in time, as in going from here to here, where you shift in space and y, as in going from here to here. It's a little shift. And you reflect in x. You see that these triangles are, they're pointing to the left, whereas here they're pointing to the right. Anyway, you see that for people who like the mathematics of symmetry, this is a beautiful playground. And this is just something that the fluid did all by itself. We did not make it do it. It just did this. And we continued. Here are strobed pictures. This is at time 0, t/4, t/2, 3t/4, where you've eliminated the basic Faraday oscillation, and you just see the evolution of the pattern as it goes from beaded stripes to hexagons, to beaded stripes to quasi-hexagons. And I can show that again. Show again. You can watch it during one period. Now it's going, I mean, during one phase, it's going, this is the beaded stripes, and then it's going to be quasi-hexagons, and then beaded stripes again. So as I said, this is beautiful, and we analyzed it with Fourier analysis. This is a hexagonal grid. You may know that the Fourier transform of a hexagonal pattern physically is also hexagonal. There's a nice duality. And during a time, during the time evolution you saw, this is how the spectrum is. First, you have a hexagonal spectrum, and then you have the beaded stripes. These are the stripes, and then these are the beads. If it were just these two, you would have a sequence of stripes like that, but then you have these little beads. When you go to quasi-hexagons, the spectrum looks like this, and so on. So this is what it looks like. This is the equivalent of this, but in the Fourier space. And then we made a phase diagram by plotting in time some different Fourier coefficients. This is this Fourier coefficient here, which is not part of the hexagon. So it starts at the beginning. Its amplitude is 0. That's T1 when you have hexagons, and then the other two the two coefficients used to represent the pattern are the sum and difference of these two. So when you have hexagons, they are equal. And then you go to the beaded stripes here. And then after that, the pattern continues like this, going from the quasi-hexagons to the asymmetric beaded stripes to the quasi. And this is, again, in phase space, using the Fourier coefficients on the hexagonal grid of this evolution that you saw before. So that was our first exotic pattern, and it left us with many questions which are still unanswered. This whole simulation, although I've shown it repeated, that's kind of cheating because we did it in a single cell and then repeated the pattern for showing it to you. So we did in this minimal domain. And what would happen in a somewhat larger domain? We don't know. Presumably it wouldn't be quite so perfect, but we don't know. We need to do this someday. In addition, as I told you in the very beginning, the basic patterns are stripes, squares, and hexagons. Is it possible that this time-dependent behavior is somehow related to a tension, a competition between squares and hexagons that everyone knows exists in a large domain? Then these bifurcation questions. Is this a heteroclinic orbit? Is this due to a Hopf bifurcation? We don't know. Is there an influence of using the rectangular grid, because our code uses a rectangular grid? Does this have an influence on our findings? So these are the questions we're left with. And now I pass to the other exotic patterns that we have found. We then my colleagues wrote a larger, this was a minimal domain, a single hexagon. My colleague wrote a larger code. They really like very much parallelization. And so they wrote a code that was capable of doing many iterations, many repetitions of a pattern. And this is in a large square, which is about 10 wavelengths by 10 wavelengths. And there you see that this square pattern completely spontaneously divided itself into a kind of waffle. What is the Russian word for waffle, Tatiana? Or bull?
Okay. So we have waffle, but scientific work about that.
No, not scientific word. It's not a scientific word. It is a.
Yes, we have, of course.
Okay, and how you say it in Russian?
Waffle.
Waffle. Okay, so you see that the square pattern just divided itself spontaneously into waffle like this, just for no reason that we know about. You see that there are 4 pieces here, and these are in phase, the diagonal ones, and these are in phase, the diagonal ones. This is a section through one of these, and you see that these are maxima when these are minima, and then when these become minima, these become maxima. And we were happy to see afterwards, after we discovered it, that this had also been seen experimentally. I guess this is, we did this in 2014, this is 1988. So I guess about 25 years earlier, this had been seen experimentally, which we hadn't known. So that is our second exotic pattern. And now our third exotic pattern, these are found in sphere. That is to say, imagine, okay, Faraday was, of course, and others were able to experimentally oscillate a layer of fluid. But imagine now something that you can't do so easily. Oh, I'm sorry, I should step back. Normally, what is done in theory or in numerics is not to have an oscillating container with a time-dependent boundary conditions and so on, but to imagine that you are, let's see, I can probably go back to this. Oh, I have a problem. Oh, well, I shouldn't have done this. That was a mistake. But I can talk, and I will say that what you do is instead you have a stationary container, and there. You have a stationary container, and you put in an oscillating, just a moment, let me get the one I want. You put in a time-dependent gravity that compensates. So you're stationary, but you have a time-dependent gravity, and that is what is shown here. You're putting in a time-dependent gravity in your analysis. And let's see, now I wanted to do, everybody can see this again now, it's okay? Hello?
Yes, it's okay. Yes, it's okay.
Good. Okay, so now I'm showing the slide again. It's a mistake to try and go too fast through slides. Okay. But now I've made the mistake of going back. Let me go back to where I was. Right, so we are going to do now something that we can only do theoretically or numerically, which is to say, to put in a radially oscillating force. So it's not shaking anymore. This is a force that oscillates radially. And you might think that would make this is a spherical drop. You might think that would shrink and expand the drop, but no, in the same way as with this, the layer, you have a pressure gradient that compensates for that. Just as the fluid can stay straight because it has although there's the oscillating gravity that does this, there's the oscillating pressure that does this. And so too in the sphere, you may have an oscillating force that does this, but you have the oscillating pressure that does this, that can keep it spherical. But just like the planar one, it can undergo instabilities where it changes its shape from spherical. And that is what I want to show you now. This is the same kind of picture as originally. These are the tongues. This is as a function of frequency, forcing frequency, and this is forcing amplitude. And now we have something very interesting that we didn't have in the planar case. In the planar case, we had different wave numbers, K. So what is a K? It measures, of course, the wavelength here. But in spheres, we have the analog to K is L, the spherical wave number, the sphere, as in the spherical harmonics. And these have different shapes. And these are the kind of shapes that we found for our drops as a function of forcing frequency. This is L equal 3, this is L equal 4, this is L equal 5, L equal 6, and so on. So it's not in the planar case, what we would have found as we increased the frequency is an increased wave number. So we would go from waves that are long to waves that are short. But here we change the L, which changes the shape. So the very first pattern we found here, this is the L equal 2 case, and this is an oscillation between oblate and prolate sphere. You see how sometimes it's going to go from a kind of football to a kind of, no, I don't mean a football, I mean a rugby ball, the American football, to something like a frisbee. Or a disc. You see how it's oscillating in this manner. Sometimes it has a long axis here, and sometimes it has a short axis. And then you may see, this is as it's just developing in time, it's getting stronger, and now it's going to be oscillating permanently at the strong way. But you may already have noticed something which is a little subtle so far, which is to say that it is precessing. It is no longer, this axis is no longer vertical, and you will see this motion a lot more now. You see this precession. You see that this is not oriented with the domain. It starts spontaneously precessing, and this is something else that we would like to understand. We've worked a little more on this, but haven't come to any definite conclusions. You see the precession. And I imagine that these are the kind of things that people who know a lot about geometry and axes of inertia and so on probably have ideas about this, because this kind of thing does not require to be fluid. It could also be an elastic thing. It's the kind of thing that Euler and maybe Poincaré and plenty of Russian geometers must have known about. When we go to L equal 3, 4, 3 and higher, we then find that the patterns resemble the Platonic solids. So I didn't, again, this is for nice geometry. What are the Platonic solids? They are, there are 5 of them, exactly 5. This has, the tetrahedron has 4 faces, each of which is a triangle. The cube, we all know, has 6 faces, each of which is a square. The octahedron has 8 faces, each of which is a triangle. And it is the dual of the cube, meaning here there are 8, on the cube there are 8 vertices, and here there are 8 faces. If you turn and there are 6 faces, and here there are 6 vertices, 1, 2, 3, 4, 5, 6. If you flatten each of these vertices into a face and put a vertex instead of each of these faces, you will get the cube. And there are 2 more, and that's what dual is. The dual of the tetrahedron is a tetrahedron except upside down. It has 4 vertices and 4 faces. The icosahedron and the dodecahedron are duals of each other. And you can see, when you think about it then, that this is a good opportunity to see this in an oscillating drop. That is to say, you have maxima that are turning into minima and minima that are turning into maxima as you go in time. And indeed, that is then what these are expressions for these in terms of spherical harmonics. That is to say, the expressions for axisymmetric states, tetrahedron, cubics, and so on. Their lowest order expansions. Here is what we got when we increase the frequency, omega, leading to an increased spherical wave number, L, leading to a tetrahedron, which oscillates between a tetrahedron and its upside down neighbor, partner. See a tetrahedron and now upside down the other way. And for a cube, we go between the cube and the octahedron. And, oh, I have the same problem that my predecessor. And so it's oscillating between the cube and the octahedron. So now you have an idea of what that looks like. For the 5 and the 6 cases, we have these nice, the 5 is not part of the Platonic solids. The 6 is. The 6, this is an oscillation between an icosahedron and a dodecahedron. So we have these very nice pictures, these nice shapes in our spherical simulations. And I think I'm getting to the end of that story. This is now my 3rd story. Yes, you may have noticed I started with L equal 2. I didn't mention L equal 1. And here is L equal 1. This is what it looks like. So it doesn't change shape. It goes back and forth. You can see that you have, if you had L equal 1, you'd have a plus on this side, say, and a minus on that side. So that makes sense. It's doing the surface is raised here and lowered here, and then it alternates in time. Raised, lowered, and so on. And that was what L equal 1 oscillation looks like. And you can see this is not, okay, I haven't been talking much about the physics of it, but these are all Faraday waves are, and it can be produced in any kind of combination of gravity and capillary waves. All of these phenomena can be seen for pure capillary, pure gravity, and any mixture. But not quite. This you cannot see for pure capillary waves because capillary waves have to do with changing the curvature, thus changing the shape, and thus that does not figure in the L equal 1 case. This is pure gravity phenomenon. And now I have my last exotic pattern, and this was unlike the others, as you saw, we the hexagons we haven't made contact with experiment except just to know that there are hexagons. For the super-squares, we saw afterwards that there had been experiments. For the drops, it's hard to do this experimentally. It's been done with kind of magnetic or electric fields holding this drop in a microgravity situation. But in general, we have not been going from experiment to numerics. This is a case in which we did. In our lab, they saw a square pattern that did this. You see how it spontaneously began to oscillate like this. They had seen the squares, and then by changing the acceleration amplitude, they got this wavy modulation, which I will show you again in the film. And we wanted to see if we could reproduce that. These wave patterns are large, have about 4 times this is about 4 times the basic Faraday wave length, and the modulation, the time, is about 20 times the basic Faraday period. Yes, I guess I should remind you, this film here that we're seeing is strobed, as we did for those hexagons. That is to say, you're not, those white dots are maxima and they would become minima at a Faraday period, but this is strobed at the Faraday period. So you only see the motion of the waves here. And so we actually succeeded in finding these waves. We have these waves here.
Sorry, Lorette, there is just 1 minute remaining.
Thank you. I'm just about at the end. I'm glad you're telling me this. So we found all of these different patterns, not just the waves, but to our surprise, we also found these other patterns. This is what they look like in the Fourier space. And hexagons have a hexagonal lattice, and these are tilted squares, which have a square spectrum. And now it's time for me to tell you a little bit about the code blue that they're very proud of. It's big code, can do up to they love to parallelize, as I said. So they've tested on this many threads, and it has many, many, many physical features. And they've done the classic things like the splash. And this is a picture of something else that they obtained with Omar Matar, who I think was mentioned in the previous talk. That's why I wanted to show this. So they've done simulations like this. And this is the end of what I wanted to tell you about. I don't really have an overarching thing, just to tell you that Faraday waves can do all these exotic patterns. Thank you very much.
Okay, thank you very much for very nice, brilliant talk. And now it's short time for questions. I see one question is in chat. It's from Michael Zaks. So in your animations, throughout the oscillations, there have been short-living needles on the surface of your tetrahedrons, cube, etc. Are they real and have physical meaning, or are they just artifacts of the graphical routine?
I hope, I mean, maybe you're talking about something that is an artifact, but I believe that some of the visualizations have velocity vectors. They're the velocity vectors, not just shown we're not just showing the position of the interface, but the velocity vectors. Is that consistent with the question you're asking?
Yes.
Okay, thank you.
I have a question. I am Valentina Shevtsova.
Yeah.
What is the role of viscosity on your nice patterns? What could be when you go to the low viscosity or high viscosity?
Yes, this is a very good question, and I have this problem has many parameters, and I think that I've pretty much shown you all the results that we have. We have not systematically varied the viscosity or any other parameter except for the acceleration amplitude. That's the main, or sometimes the frequency, and all those. You know, I feel that many people could be studying these and answering this very question.
Okay, thank you.
It would raise the threshold, that's for sure. But what else, what the effect it would have on the patterns, I don't know.
Okay.
Okay, other questions, please?
What about localized patterns?
This we have not seen and we have not sought. You mean in a plate where we would have just one look? I have someone from Chile came to work with me, and he seems to have localized patterns, but he has not really pursued that. And I will just say that's not something that we have seen or are seeking right now. But it's an interesting question too.
Mm-hmm.
On my side, it's not question, just curiosity.
Yes.
Are you going to compare this oscillation of sphere with experiments in microgravity for drop levitation, or there is also a ground experiment in magnetic levitation?
Okay, naturally, like we listed all of these things in our introduction, and we know that there have been these things, but we have not compared these things systematically. I'm afraid we should, but the student finished his thesis and we did not pursue this further. It would be a very good thing to do. I would like this to be the beginning of a whole research endeavor where we would vary parameters, where we would compare with experiment. But it's a good thing to do. I agree.
Okay, thank you.
Okay, other questions, please? So, in fact, some questions were the same then from me. So, also, we would like to discuss with you later, because just now we do not have time, about the conditions, dispersion relation, validity. Yes. So this is very important for us and maybe we discuss, not maybe, but just discuss later. I suggest this. Okay.
Yes.